We're going to connect continuity with openness here. Well, this theorem says, suppose you have two metric spaces, a mapping F from X to Y is continuous if and only if the inverse image of any open set, like V in Y, is open in X. Let us begin proof. Let X and Y be metric spaces, and F maps X to Y is a continuous function. Okay, so we have continuity. Our goal is to show that for any open set like V in Y, inverse image of V is open in X. What's the meaning of that? It means that we need to show that any point in inverse image of V is an interior point. What's the meaning of that? It means that we need to show that for any point in inverse image of V, there is a neighborhood included in inverse image of V. Let's put a question mark here. This is our goal. This is what we're trying to prove. So let us begin. Suppose you take a point like P in inverse image of V. By definition of mapping, f of P belongs to V. By assumption, V is open. So f of P is an interior point of V, or any neighborhood of P is included in V. So far we have this information. What's the meaning of that? It means that, well, there is a positive epsilon such that the distance between f of P and any random value like Y is less than epsilon, and Y belongs to V. By the definition of continuity, by the assumption f from X to Y is continuous. So for any positive epsilon, we can find a positive delta such that as long as the distance between X and P is small, then the distance between f of X and f of P is also small. Okay. Let's take a look at the simpler version. Here you have two spaces, X mapped to Y by F, and V is open in Y. So you have inverse image of V. Let's make it a little bit larger so you can see what's going on. Inverse image of V. We are saying that since V is open, there is an open interval around f of p, for example, the set of all y values such that the absolute value of y minus f of p is less than epsilon. That epsilon can be a very small number, like 1 over m. And this open neighborhood, open interval, is included in V. By continuity, there is an open interval around P such that the distance between X and P is very small. Well, that small value can be written as 1 over n. But this interval, by continuity, is mapped to another interval, right? Which is mapped to an interval around f of p, which implies that the distance between f of x and f of p be very small. The meaning, in simpler words, so it means that we can arrange these distances to be very small. We're just trying to find an interval, right? Interior points, it means that we are looking for a neighborhood. We can arrange this delta to be so small that the distance between f of x and f of p be very small, as you can see here. This implies that the interval x minus p less than 1 over n be included in inverse image of V. So it means that we found a neighborhood around P that is included in inverse image of V. So V is open. So in more general version, we can arrange the delta to be very small. As you can see, your delta 1 over n, and you can take this very small value. That's the interval, which in this case is going to be a neighborhood, the open neighborhood around P be included in inverse image of V. So inverse image of V is an open set. So your x-axis and your y-axis. Suppose you have your continuous function f. This is your p, and then you have your f of p. Open interval around p, open interval around f of p. And V is an open set in Y. Its inverse image includes, let's remember the definition of inverse image. The inverse image of V is the set of all x values such that f of x belongs to V. That's the definition of inverse image. So we are looking for all of those x values such that f of x belongs to V. Because of continuity, we can force this delta to be very small. Why is that? Because we already know f of p has an open neighborhood. Conversely,